Hello, honors pre-calculus students. This is Mr. Hazelhorst coming to you live from room A08. Today we're going to build off of yesterday's lesson of system of inequalities, and we're going to take the next step of that and cover what's known as linear programming, which should be a review for you from your honors algebra 2 days. But we do want to take the time to go through. It's an important concept in math, and so we want to go through and take some time to review this here today. Again, if you have any questions over this video or this section, I want to encourage you to utilize your textbook. Look closely at the example problems that they go through, and as always, use your classmates as a resource since they're there with you today as well. All right, well, let's jump right into it today. When we talk about linear programming is the idea of optimizing some equation based on a set of constraints. All right, so that when we talk about constraints, you can think back to our systems of inequalities yesterday in that video that we learned, that we went through, and all that information that was covered. You're going to see all that pop up again today. All right, but again, we want to go through this idea of optimizing a linear objective function. Okay, when we talk about optimizing, what we mean is we want to find the minimum and or the maximum value depending on the setting or the problem. All right, so we're going to start out simple here today. We're going to start out with just a couple of basic examples. But one thing we should make note of is when we're looking to find those minimum or maximums, they're going to occur at the vertices, right? So think back to yesterday's video again and the examples we went through. And vertices, remember, are those boundary areas, those points of intersection, okay? So let's jump right into it today with an example problem. So in this problem, we want to find the minimum maximum of our objective function, which is z is equal to 3x plus 2y. So we want to optimize variable z, which is constrained on variables x and y, all right? So we're given the constraints here that we need to follow. So what we need to do to begin with is we need to find the solution region along with our vertices so that we can then plug them into this optimization formula. All right. So let's go ahead and just graph the system of inequalities. The first thing I'm going to make note of is that all my inequality symbols are all greater than or less than or equal to. So I have solid lines in all my graphs. And in linear programming, we're generally going to see all greater than or less than, include the or equal to part, because those vertice points have to be included in the solution region. Okay, so let's go ahead and graph this. Again, this problem, x is greater than or equal to 0, and y is greater than or equal to 0. So essentially, we're containing our entire solution set to the first quadrant once again. All right, so let's go ahead and graph my two linear equations. I'm going to go ahead and just use the zeros, the intercepts, to help graph that. So in my third function here, x plus 2y is less than or equal to 4. If I go ahead and plot those points, my x-intercept would be at 4, and my y-intercept would be at 2. And so we're going to go ahead and sketch that line in here. Again, pretend it's straight. And again, remember, we know that we're already contained in the first quadrant, so I can just follow that there. All right. My next one, I need to recognize here again if I plot these points. So we've got x minus y is less than or equal to 1. So if I go ahead and find these intercept points, so my y-intercept would be at negative 1. My x-intercept would be at positive 1. And so we can see the slope here is 1 over 1. All right. And now I'm going to kind of test a point so I make sure I know what my correct solution set is here. So I'm going to go ahead and test the point 1, 1. That would be an easy point to test here. So if I plug 1, 1 in all my inequalities, so 1 going into x, 1 is greater than or equal to 0. That is true, so it works for that inequality. If I plug 1 in for y, it is also greater than or equal to 0, so it checks out for my second inequality. If I plug 1, 1 into my third inequality, I'd get 1 plus 2, which is less than or equal to 4, so that checks out. And if I plug 1, 1 in, we get 1 minus 1 is 0. Check that off. All right. And so we have this solution set that would be defined here. All right. Now, at this point, we haven't done anything different than yesterday, right? We've just graphed all of our constraints and found the solution region. Okay. But what we would need next is we need to identify the vertices. So if I take a look at all my vertice points, right, what are all the points of intersections that bound this region? Well, I have a vertice point at 0, 0. I have a vertice point at 0, 2. I have a vertice at 1, 0. And I have one here at 2, 1. So now I need to take and plug all of these values into my objective function, all right? So if I just take just these 4 points and plug them in and solve for z, that'll tell me what the maximum and minimum of z are based on these constraints. All right, so let's start out with 0, 0. That's the easy one. So if we plug 0, 0 in, z comes out to be 0. If we plug in 1, 0, we get 3 plus 0, so z is 3. If we plug 2, 1 in, we get 6 plus 2, so z is 8. And we'll plug 0, 2 in, so we get 0 plus 4, so z is equal to 4. All right? And now all we have to do to determine the minimum and maximum value is just look at the values of z utilizing, again, just these 4 vertices. So I can see that the maximum occurs here at the point 2, 1. Right, that's when z is its highest value of 8. And the minimum occurs here at 0, 0. Z's value then is 0. All right? So that's an example of just a simple linear programming problem, right? We're given an optimization function, we plug in the values, we're good to go. Now, one thing that we should comment off of this slide is this is an example of a bounded solution region. But if we just went through and changed some of these inequality symbols, we could create an unbounded solution region. And the thing to recognize there is, depending on the direction of how it's unbounded, is that we may not have a minimum or we won't have either a minimum or a maximum. All right? So just for example here, let's say, and I'm just utilizing our graph here just as an example, let's say that this was our solution region, right? This unbounded region. Well, this would not have a minimum value because based on how I'm shaded, right, it would just keep going on and on and on. All right? But it would have a maximum value occurring at whatever its vertices are here in this problem. All right? So that's just an example. You might deal with that. You'll see that on occasion in a linear programming problem. All right, let's get to a story problem then. Now, we're going to utilize the same problem that we used yesterday. All right, so I'm going to do this here just to save us some time, and that'll give you some more time to work on your homework assignment. So for those of you who were not here yesterday, I'm just going to throw a bunch of inequalities up here real quick that we figured out yesterday. And if you were not here yesterday, I would recommend you go online to my classroom website, go to the pre-calculus videos page, click on Chapter 7, and watch the 7.5 video. All right, the 7.5 video explains where all these inequalities that I'm about ready to write up on the board come from. All right, those who were in class yesterday, again, you saw this problem yesterday. Today we're just going to add on one layer at the end. So real quick, just to recap what we came up with yesterday. All right, we had two variables, x and y. X was representing the number of cups of drink X. And y was representing the number of cups of drink Y. All right? And then we wrote 5 inequalities yesterday. We said that 60x plus 60y is greater than or equal to 300. And this was representing our calorie information. And then we had 12x plus 6y is greater than or equal to 36. That was representing our vitamin A information. And then we also had 10x, that's an x, plus 30y is greater than or equal to 90. That was representing all the vitamin C information. And we also said, okay, X, you have to be greater than or equal to 0, and Y, you have to be greater than or equal to 0. We can't have a negative number of cups of drink. And so then we graphed all this information. So if I just throw those graphs up here real quick, again, the X and Y axis, we're serving as a boundary region. So again, we have to be contained within the first quadrant. And then our first inequality, using our X and Y intercepts, my second inequality, using again our X and Y intercepts, and then our third inequality, again, using our X and Y intercepts. And we have the solution region up here. All right. So this is all the information that we came up with yesterday. And so again, we want to identify those vertice points. So we had 4 points that we identified. We had the point 0, 6, right? So 0 cups of drink X, 6 of cup Y, or drink Y. Then we have the vertice point 1, 4. We have the vertice point 3, 2. And we have the vertice point 9, 0. All right? Now, we need to optimize this function. So in order for us to do that, we first have to write an optimization function. So let's go back into the problem. And if you look today, there's a little bit of new information. So let's go to the question at the end. It says, how many cups of each drink should be consumed each day to obtain an optimal cost? All right? And still meet the daily requirements. So that's what we're trying to optimize, is we're trying to optimize cost. And if we go back and look, we're told some information that drink X costs 12 cents per cup, and drink Y costs 15 cents per cup. So we can write a very easy optimization function, right? Cost would be equal to 12 cents times X plus 15 cents times Y. All right? And now we can take and plug a whole lot of this information in. All right, so if we just take these 4 vertice points and plug them in to our cost equation, what we're looking for here is the minimum cost, right? If we optimize costs, we're going to keep costs the lowest that it can possibly be. So if we plug 0.6 in, we'd come up with 90 cents. So our cost here, 90 cents. If we plug 1.4 in, we'd end up with a cost of 72 cents. If we plug the 0.32 in, we end up with a cost of 66 cents. And then the 0.90 would give us a cost of $1.08. Right? So if we want to optimize our costs, if we want to minimize our costs, if we combine 3 cups of drink X with 2 cups of drink Y, that will give us all the daily requirements that we need to meet in terms of calories and vitamins, yet also cost us the lowest amount. And that's the idea of linear programming. Now, you might think, well, what's the big deal? Why would anybody want to do that? If I was running a hospital and I was serving thousands upon thousands of patients day after day after day, a drink that we needed to make sure they had the right amount, right? Well, being able to spend the lowest amount on that drink could save my hospital lots of money over the course of the year. And it's simple things like that that are a great application of mathematics in the real world. All right, well, there is linear programming for you today. Again, if you have any questions, I want to recommend that you look back through your textbook in this section, Chapter 7, Section 6, or use your classmates for some help. So here's your homework assignment today. I hope you guys have a great day. If you need to go back and re-watch this video, just know that it is posted online in the pre-calculus section under pre-calc videos. and just go to chapter 7. All right, you guys have a great day, and I'll see you soon.